Hello. This tutorial is to help you work through the Biology 102 Critical Thinking Assignment number 2. And the purpose of this assignment is to help you learn some basic statistics and how they are applied in a scientific setting, and then to use some of this information to apply critical thinking skills to kind of a real life situation. So to think about statistics and some of the techniques we're going to use in a different way, I want you to consider how science generally proceeds. Normally, we look at observable facts and we try to interpret those facts. But each of us has a different way of looking at things. Each of us has a different way of determining whether or not something is important or whether or not there's a big enough difference, say, between two things for that to be real. And what we try to do with statistics is we try to come up with a scenario by which all of us can agree on when the results are good, when they're solid, or as we say in statistics, when they are significant. So think about this. If you flip a coin and it lands heads, would you be surprised? Most people probably wouldn't. There was a 50% chance of that happening. If you flipped it again and it landed heads again, would you be surprised then? Well, there's a 25% chance of that happening, 50% for the first time, and then 50% of that for the second time, so that's a 25% chance. If you flipped heads a third time, there would be a 12.5% chance of that happening, 1 out of 8 you'd expect. And some people would start to be surprised there. 4 heads in a row, a few more people would be surprised. 5 heads, yeah, a lot of people would be surprised. 6 heads, there might still be some holdouts that aren't surprised by that result. And that's the thing that statistics are there for. We want a consistent way that everybody determines when they're surprised. And so when we say a result is significant, we say that that scientifically speaking, we should be surprised by this result. And so that's what we're trying to do. So I want to call your attention at this point to the critical thinking assignment sheet itself, which I have up on the screen here. And I'm going to scroll down a little bit and talk about some of the different tools that we're going to be using here, most of which we're going to be using, a couple that we aren't. We're going to be talking about scatter plots, which allow us to see if two things are related to each other. We're going to be talking about the trend line, which is a mathematical model that we can put on a scatter plot to derive some important information. And finally, we're going to look at the histogram, which is used for patterns in abundance. Now, we're not actually going to use all of these different tools here, but we are going to use the scatter plot and the trend line, okay? Then we want to look at some various statistic tools, and in particular, we are going to be looking at the t-test here. We'll also talk about the correlation coefficient, and we're not going to really use the chi-square test or the ANOVA test with this data. They're not, these data are not really amenable to using those two tests. But from the standpoint of a beginning scientist, knowing how to do the t-test is really pretty important. So let's go ahead, and I'm going to scroll down a little bit further and talk about some of these different things. Okay, if you've taken Biology 105 or 106, you already know how to do a trend line. You use that to figure out the rate of respiration in your yeast, okay? Generally, the slope of the trend line shows the relationship between things. Biology 105, it was the rate of reaction. But basically, it shows the relationship between the two sets of data that we have. The other thing we want to know is the correlation. The correlation is the strength of the relationship between two variables. So here we have a sample graph, completely made up numbers. And on the x-axis, we've plotted the length of some hypothetical organisms called snouters, and the weight is on the x-axis or the y-axis. So basically, what we're trying to see is there a relationship between length and weight in snouters? Or in other words, the longer a snouter is, does it weigh more? Okay, and that would seem to be obvious. Generally, as animals get longer, they also tend to weigh more. So you can see we have 4 data points plotted there. And then we have this weird little equation on there. So let's take this apart a bit at a time. First, we had these 4 points plotted there. This line is not actually drawn between those data points, but it is put on top of them. It is what we call a trend line. Okay, and that trend line is a mathematical model that tries to draw a line that will come closest to all of the dots in the data set. And when it does that, it has characteristics. We can describe a straight line in the equation y equals mx plus b. You probably remember that from algebra or something along those lines. So here's y, and there is m. In this case, m is equal to 0.42. There's our x. Plus 4.711. This last part is the y-intercept, and that says that if we extended this line over to the y-axis, it would cross it at 4.711. We're going to pretty much ignore that. This part right here, the slope though, that's important. That says that for every centimeter that you make a snouter longer, you're going to increase its weight by 0.2244 grams. Okay, that's the relationship between length and weight. And then we have this other thing here. This is not part of the same equation. It's a separate equation. And it says R squared is equal to 0.9973. In statistics, this R squared number is a measurement of how close each of those dots is to the line. If they were all on the line, then R squared would be equal to 1. You can see they're pretty darn close. Now, technically in statistics, we don't use the R squared to tell how close things are to the line. We use just R. But if you take the square root of this, it's still going to be very, very close to 1. And that means that these data are a very good fit to the line. Okay? So, and you can see that by looking at it, but this gives us a number as to how close they are. Okay? Now, this particular relationship is what we call a positive correlation. As the X values increase, the Y values increase as well. But that's not the only possibility. And because we have this equation up here, we can use it to extend this line in different directions. For instance, if we wanted to know if a snouter weighed 16 centimeters, we could extend this line by eye and say, yeah, it's going to be about right up there, which is getting up to about 11.5 grams. But we can calculate it directly. We can simply put 16 in for X. So if we take this equation, y equals 0.4244 times 16 plus 4.711, that comes out equal 6.79 plus 4.711, or 11.5 grams. So you can see that the trend line does a number of things for us. It shows us the relationship between the two units. That is this number, that's the slope there. And it also allows us to extend the line into areas where we don't have measurements. Now that may or may not be valid. For all we know, this line goes up or down on the other side of it. But assuming that it remains the same, then we'd have a good relationship there. And with the R squared value, we can also say that tells us how good our model is. So when we say it's going to be 11.55 grams, we are pretty certain it's going to be very close to 11.5 grams. If this number was smaller, then we would know that that 11.5 grams is a little bit more of a guess. So let me scroll down here a little bit, if my computer lets me. Here's 4 different graphs with 4 different trend lines on it. Graph A is the one that you just looked at. And let me zoom in on it a little bit here so you can see it a little bit better. That's the one we just looked at. And that's what we call the positive correlation. As Y increased, or as X increased, Y increased. When we look at graph C here, we see a negative correlation. In this case, as X increases, Y decreases. Now, this would make no sense for real animals. This is just hypothetical here. You also notice a couple things. One is in our equation, there's now a negative sign right there. Another thing that we see is that the R squared value is smaller. Now remember, you take the square root of that to get R, and that square root's still going to be 0.9 something. So it's still a pretty good model, but you can see these dots are further away. Okay. B shows an example where there's very little slope. As length increases, the weight increases, but just slightly. And in this case, you can also see the R square is not a very good fit at all. And finally, we have a positive correlation, but it has a much steeper slope. And it has an intermediate range for R squared, although again, R squared here is going to be, or R is going to be between 0.8 and 0.9. So these graphs all are telling us some different things. If we look at graph B, for instance, we see there's a relationship. It's not a very good model. That's what the R squared value says. And it doesn't tell us a whole lot, because basically, if a snouter is 1 centimeter long, or if it's 15 centimeters long, it's going to weigh somewhere between 7 and 9 grams. So knowing how long it is doesn't really tell us how much it's going to weigh, okay? Because it has a very flat slope. On the other hand, over here, we have a much steeper slope, and just a small increase in length leads to a big increase in weight. Again, it's kind of useless, because if we, as long as we're between, say, 9 and 11 centimeters, if we know that the weight is between 11 and, say, 5 grams, we know that the snouter is going to weigh, or it's going to be between 9 and 11 centimeters long. Okay, but it's a little bit better relationship. So these are the four possibilities, four possibilities we could have. We could have just kind of a regular positive slope or negative slope. We could have fit that's very tight or a little bit looser, and we can have very flat graphs or very steep graphs, and they all tell us a little bit different thing about our relationship. So those are some of the things that we might see. Okay. I'm going to scroll down a little bit more, okay? So to summarize this, 3 key things to examine: the direction of the slope, is it positive or negative? The steepness of the slope, how strong that relationship is, and what the R square value is, how good that model is overall. So again, positive or negative correlation, the steepness of the slope, and then how well it fits. These graphs here just explain a little bit more about what a flat slope versus a steep slope does for you. Okay, that's the effect versus the correlation. So that's it for the graphical analysis that we're going to do. Now I want to talk about the t-test. Okay, and this is a very important statistical test. It helps you answer the question, are the means or the averages of 2 data sets the same or not? Now, in statistics, we often can't prove something, but what we can do is reject a hypothesis. We can disprove something. And so with the t-test, what we're doing is we're setting up a hypothesis that the 2 means are equal to each other. And if we can reject that hypothesis, that supports the idea that the 2 means are different, that there's something going on here, okay? So what we're going to, the way you might want to think about that is, let's say you went to a big city, let's say Chicago, and you show up in Chicago and you want to know how tall the people are in Chicago. So you go to a big arena in town and you wait for people coming into the event. Now, let's say in Chicago that day, what was going on was the orchestra playing, Peter and the Wolf for the elementary school kids. And so you're standing there at the door, and you've got, a tape measure on the door like they have at the door in the 7-Eleven, so they can see how tall the robber is when they leave. And you're measuring the kids, and it's 4 foot, 3 foot 5, 5 foot, 4 foot, and a teacher walks through at 5'6", or maybe a tall teacher at 6'2", or something like that. And you take that average, and you're going to have a pretty small number at the end of the day when you take an average of those 100 people. On the other hand, let's say you go to Philadelphia and you go to their arena, but the event that you're at is the city basketball tournament, and you're at the gate where the teams are coming in. And they're coming in 6 foot, 5'9", 6'7", stuff like that. You're going to get a very different number. And the question we have then is the number that you're seeing between those two cities, is that a real difference, or did you just have really bad luck in your sampling? And that is what the t-test is going to tell you, okay? So what you want to do is the first thing you need to do is set something called an alpha value. And the alpha value says this is the chance that you're going to erroneously conclude that the means are different, when in fact you just had bad luck in sampling. And generally in biology, we set it at 5%. In sociology or psychology, they might set it at 10 or 15% because their data are extremely variable to begin with. In physics, they may set it at 1% or 0.1% or even lower because they're making very precise measurements. So let's take a look at what a t-test looks like if you run it through Microsoft Excel. Okay, so this is a t-test. It assumes unequal variances. We'll talk about that later. Excel gives us a printout. It tells us the mean or the average of the length in millimeters and weight in grams, okay? It tells us the variance. On average, how far away was each individual from that average? You know, and this is saying most of them were somewhere between 24 minus 7.5 or 24 plus 7.5. The weight between 0.133 grams and 0.135 grams, because this is the variance here. We made 61 observations. We took 61 organisms and measured their length, and we got the weight from those same 61 organisms. We hypothesized that there's no difference between the means. That's our null hypothesis, the one we're trying to disprove. Don't worry about DF, that's degrees of freedom. It's usually less than the number of observations. And the computer spits out something called a t-stat. Okay, this t-stat is the measurement of how much difference we're seeing. And the thing about the t-stat is that we need to know, is the t-stat bigger or smaller than the t-critical value? If it is bigger than the t-critical value, then we reject that hypothesis that the means are different. And we believe that, or that the means are the same, and we believe that the means are different. So in this case, 68.6 is much bigger than 1.67 or 2.0. So we can reject the hypothesis clearly. What is our chance of being wrong? Well, remember, we were going to be happy if our mean was less than 5%, 0.05. Well, in this case, our chance of being wrong is 4.91 times 10 to the minus 59. So you'd have to put 59 zeros in front of that 4, 0. And then 59 zeros, and then that 491. That is a very, very small chance, okay? A snowball in hell would have a better chance than that, I think. Now, this one tail and two tail, you need to make a decision as to which of these you're going to use before you do the test. If you expect one or the other to be bigger, let's say you have two gardens and you're fertilizing one garden and you're weighing the fruit at the end of the summer to see which garden grew the most. You would expect the garden you fertilized to have a bigger weight. In that case, you would use a one-tail test. On the other hand, if you just had two gardens and you didn't know if one had been fertilized or not, or if like one garden was on top of a hill and the other was on a slope and you didn't know which would have an advantage in that situation, then you would use the two-tail test, okay? So again, the main thing though with the t-stat is if the t-stat is bigger than the t-critical, okay, then you reject the hypothesis that the means are the same. Whoops. And that means that the means probably are different, okay? And this explains how to interpret that. So if you forget later on, you can read back through that. Okay, so that's the background that you need to know to do this. So let's turn to the assignment itself. Okay, there's a book by a guy named Paul Kendi called Preparing for the 21st Century. Now, he wrote this in the 1990s, so we're well into the 21st century, but his basic argument is still being used today. And his argument was that increasing female literacy can help combat world overpopulation. And what we want to do is we want to look at this statement critically. Okay, we want to see, is that true from a critical sense? And on page 341 of his book, he states, as United Nations Population Division statistics show, in country after country, there's a strong inverse correlation between the adult female literacy rate and the total fertility rate. And he goes on to say, the evidence overwhelmingly suggests that when education is widely available to women, average family size drops sharply and something called the demographic transition sets in. Okay, sounds good. You might be reading the book and say, yeah, okay, I'll buy that. But again, we want you to be a critical thinker. Okay, so let's take this apart. Correlation, he's saying that there's a correlation, right? We know that correlation is not the same as causation. You've heard people say that. Just because two things have a relationship doesn't mean that one causes the other. And so if he's going to propose that, he also has to, if he's going to say there's a correlation and say that literacy decreases the fertility rate, then he has to show correlation. And he does do that in his book. He says things like, education takes up time and postpones childbearing. And educated women choose to have fewer children to maintain a higher standard of living. So he proposes that, and those are things we'd have to look at separately. We're just going to look at the numeric part of his data. And for some reason that got moved. So this is the data that Kennedy shows, this table right here, this adult female literacy rate and the total fertility rate. And if you look at it, okay, these countries here have pretty low literacy rates. The best they do is about 5.58% of the female population can read. And if you look at their fertility rates, the lowest one there is about 5.6. That's 5.6 children per woman. That's what we mean by fertility rate. The other group of countries Kennedy gives us, their fertility rates bottom out at 0.79 and they go up to 0.98, and the literacy rates and the fertility rates range from 1.7 to 2.7. So 1.7 to 2.7 babies per woman. Okay, so at first glance, that's, that looks pretty darn good, doesn't it? Now, scientists, though, they don't like to look at tables like that. First thing they're going to do is take that data and they're going to graph it out. And so that's what I did. And that's what you're seeing in this graph. I'll make it a little bit bigger for you here. And you can see that in this graph, I put the trend line on there. Here were the low literacy rate countries, including this one. And here were the high literacy rate countries. You can see these high literacy rates do have low fertility rates. The low literacy rates do have high fertility rates. And the relationship is a negative relationship. As literacy goes up, fertility comes down. And is the model fitting pretty good? Yeah, 0.91 R squared, that's a pretty good fit. So at first glance, Kennedy seems to be making a strong case here, although he could have made his case stronger if he would have used a graph. Okay, so the other thing we want to know, though, is are these literacy rates here different from the literacy rates here? And are the fertility rates here different from the fertility rates here? We've got correlation, we've got a good model, but what we don't have is a statistically significant difference between these two sets of numbers. Okay, if we average out the fertility rate here, it's 6.6. And if we look at the other country, it's 2.1. That's, greater than 3 times in the low fertility, from the low fertility countries to the high fertility countries. They seem different. Okay, in the assignment, I'm going to ask you, is there a significant difference there? And why do you say that? And some people say, well, of course there's a significant difference because one's 3 times bigger than the other. That means crap. That doesn't mean anything at all. You have to do a statistical test. So we need to do a t-test. And if you apply a t-test to those numbers, we get our high fertility and low fertility. Those are the means or the averages. There's the variance. We had 6 high fertility countries and 5 low fertility countries. The degrees of freedom was 9, okay? And our t-stat was 13.79, actually 13.8 or even 14. Okay, now the question for you, before I point out the answer is that a significant difference? So before you can look at the p-values and the t-critical values, you have to say to yourself, is this, are we going to use a one-tailed or two-tailed test? So think about that for a second. Do we expect one of these to have a higher fertility rate than the other? Now, hopefully after thinking about that, you said, well, duh, we're calling the one high fertility, so we expect the one to be bigger than the other. And that would mean we look at the one-tailed numbers here. And you can see that 13.8 is far bigger than 1.83. So we reject the null hypothesis that the means are the same. We say that these are statistically significantly different. And our chance of being wrong is 1.16 times 10 to the minus 7. Okay, it's not 59 zeros, but 7, and that's still quite a few. Okay, now, before we get to the actual questions here, I need to show you how to run a t-test. So here are the instructions, and I'm going to take you through how you do this, okay? The first thing we need to do is we need to get our data into Excel. So I'm going to go back up here. There's no reason for me to go and type this. I'm just going to highlight the data in Word. I'm going to right-click on it and say copy. And now I'm going to switch over to Excel, which has been sitting here all this time waiting for us. And I don't like to go up into A1 because I always forget to put something in and then I have to insert a space. And I don't like to be in column A because I'll forget some over there. So I'm going to come over here and give myself a little room. And I am now going to right click again and put in, look at the paste options. And I'm going to, I'll just keep the source formatting. And so now I've got my data pasted in there. Okay. Now I need to do a little bit more to it because I need to compare these numbers to these numbers. And I need to compare these numbers to these numbers. And the way they're arranged right now, it's not the easiest way to do it. Okay. So what I want to do is I want to take my literacy rates and I want to divide them up into two groups. So I'm going to start up here. Like I said, I always need room above. And I'm going to put in literacy to remind me what it is. And I'm going to put in high, or excuse me, low. And then I'm going to put in high. Okay, and then, and just to make this a little more readable, I'm going to center all those, and I'm going to merge these together. You don't have to do this, but I just want you to be able to read a little bit more. Where's my merge? Merge. There we go. So I have low and high. Oh, I didn't put center. There we go. And now I'm going to copy the data over there. So my low literacy numbers are right here. And so I copy and come over here and I right click again and paste. Okay, there's my numbers. And now I come down and get these. I can come up here and I can do the, oops, I can't do that up there. I already have that highlighted. So I come here and go copy. And now I could come over here, whoops, here, and do paste. Okay, so there's my numbers that are in there for the literacy rate. And now they're set up so in a way that I can use them pretty easily. So what I'm going to do is I'm going to go up to my, my toolbar here, my menu bar, and I'm going to go over to data, and I'm going to use data analysis. Now, the first time you go to use Excel, you may not have data analysis checked there. So watch carefully what I do here. I'm going to click on File. I'm going to come down to Options. I'm going to come down to Add-ins. and I'm going to say, oops, yeah, add-ins. And down here it says manage Excel add-ins, and I say go. And I want to make sure that these two boxes here, the analysis tool pack and the analysis tool pack VBA, that those are both checked. If you didn't have the data analysis tools, it was because these weren't checked. When you click OK, you go back in here, and now when you go to the data tab, you should have data analysis. I click on data analysis. It brings up a whole bunch of tests. I'm going to go all the way down to the bottom, and I'm going to do the t-test to sample assuming unequal variances. Since I don't know if the variances are equal, that's one I have to use. Don't worry about the paired sample. We don't have the right data to do that one at all. And I say, okay. It brings up this bar. Now I need to highlight the areas that I want to use. So I'm going to highlight my low literacy, including the label. That helps. And then I'm going to click down here for variable 2 and select the other ones. And they can be 2 different sizes. That's not a big deal. My hypothesized mean difference is 0. I do have labels in there. I had the low and the high. You need to be careful. If you don't click the low and the high and you just click these, then don't click on labels. Only click on labels if you included the labels. Alpha is equal to 0.5. And here comes the tricky thing. I want to put it on the same sheet. So I'm going to click on output range. But when I do that, it jumps into a weird place. And I want to make sure I click here. And then I want to come in here and I want to pick an empty spot with nothing below it or to the right of it. So I'm going to go right there, J6. And when I click OK, then it puts all my data in there. Now it's a little bit hard to read like that. So what I'm going to do is, while it's all highlighted, I'm going to come up here and I'm going to didn't work. I'm going to highlight these 3 lines. I'm going to right click up at the top and, excuse me, I don't need to right click up top. That's what messed me up. I'm going to go to Home, come Format, and Auto Fit Column Width. And it will spread things out a little bit. And now we can see our data here. And I'm going to zoom in on it a little bit so we can see it. Our means, 0.16, 0.9, variance, observations, degrees of freedom, and so forth. Okay, now do we have a significant difference between the means? Ignore this negative sign. The fact that that sign is negative simply means that the second one was bigger than the first. So ignore that completely. 8.16 is bigger than our t-critical. Remember, we decided to use one tail. Okay, it's bigger than that. So we reject the hypothesis that the means are the same. Our chance of being wrong is 3.9 times 10 to the minus 5th. That's well less than 0.05, okay, which is 5 times 10 to the minus 2. So we've got a very small difference, and we would expect that we've got a significant difference, okay? So that's how we do the literacy. Now, if you remember, okay, that is the literacy. We already had, in the Word document, we already had the fertility values there, and these were the literacy values. And I could even come in here and put in here something like this to make it more clear that we're talking about literacy values. Or I can put it over top of these two. I could merge these cells and say literacy. So there's no question as to what I have, what kind of data I'm dealing with. Okay, I hope you followed that. Here are the instructions to do that step by step, okay? And it shows you how to do it in Excel 2007. I just showed you in the newer version of Excel. And it shows you how to manage the add-ins there too, okay? Now, the important 2 biggest mistakes you can make here are confusing literacy and fertility. When I say test fertility, test fertility. When I say test literacy, test literacy. Remember, literacy cannot be greater than 1. You can't be more than 100% literate, okay? You can't have a population that more people are literate than there are in the population. On the other hand, you can have more babies than one. So fertility numbers can be bigger than one and usually are. Okay, the other thing is if I ask you for a significant difference between the means, don't tell me, oh, it's significant, one's 3 times bigger than the other. Do the statistics and interpret the values, okay? So in other words, on question number 8, run the t-test and interpret it or you're gonna lose some points. And again, I'll do some help sessions if you need them, but what I'm doing right now is basically the help session. So here's the critical thinking assignment. This is the only page that you should be turning in, okay? You type in your name, and then we can get rid of some of those, okay? Then it says in the graph on page 5 of the assignment, one data point sticks out. What is the literacy rate in the country represented by that point, and what's the fertility rate? So if we go back to page 5, we're looking at this graph right here. There's our data point sticking out. Now you could estimate the literacy rate by coming down to here and you say, well, it's going to be a little bit more than 0.5. And the fertility rate's going to be somewhere between 5 and 6, but that's the hard way to do it. We could also come over here and say, oh, geez, that one right there has a literacy rate of about 0.58 and a fertility rate of about 5.6. Maybe that is it. So we would come down here and we would type in, you know, literacy rate 0.58. Okay, you get where I'm going? So you shouldn't have a problem with that one. What was the slope of that regression line? Well, you go back here and you look at the equation for y equals, and you look for the number in front of the x, and right there's your slope. Don't forget the negative sign, and you type that in. Okay, you guys can see by now, this is not going to be real tough. You've already done the hard work, okay? What is going to be the fertility rate in a country with a literacy rate of 0.45? So you need to show me the work here. So in other words, you would say something along the lines of y equals, and then you have the slope of the line, which was minus 5.58 or something like that. Make sure I've got the right number there, times 0.45, which is our x, and then plus the part that came after that, the y-intercept, which would be 7.3454. You don't need to go crazy with the decimal points. You know, something like that. Do the calculation, type it in down here, you know, equals, and then, you know, type the answer back here. What are the mean adult average female literacy rates? Well, that's a real tough one. We just calculated that. Here's the one for the low and here's the high. So you just need to copy these back over to there. What type of correlation is represented by the figure on page 5? Well, that's where you need to look at that. You know, is it positive or negative correlation? I'll leave that up to you. Then in here, I want you to type a paragraph explaining the nature and strength of the correlation. So this is where you'd say if it's positive or negative, you would talk about you know, how steep the slope is and use the actual numbers. You've got numbers here. So tell me how steep is the slope. Tell me how good a fit the line is to the data. Talk about the R-square value, okay? So that's a paragraph. It doesn't have to be a super long paragraph, but explain what's going on there, okay? Is there a statistically significant difference in the mean fertility rates in the high and low fertility countries? We already said this, but you go back up to this table, remember what I said, or press rewind and you've got the answer for that. Is there a significant data? And talk about it in terms of the t-stat and the t-critical, and make sure you're using the right 1 or 2 tailed test and so forth. Same thing for literacy, okay? But for this one, what you need to do is you need to go back into Excel and grab your data here and do a copy, and then come over here and do a Control V and paste it in there, okay? And you might need to come back in here and let me see if I can find the, where's it at? There we go. Stretch this out a little bit so that your those numbers aren't getting off. They're actually, you got enough decimal points, you kind of get rid of them. It's kind of acting up kind of weird. There we go. So you can rearrange things a little bit. And then below this, well, now you've got that pasted in, then, you know, type in your paragraph. And by the way, never split a graph across 2 pages. You can easily go insert, there we go, page break, and then come down there. Okay, then 9 and 10, these are completely on your own. Does Kendi make his case? Type a paragraph outlining your viewpoint. What questions does Kendi's presentation raise for you? Write a paragraph describing the questions this work raises. Okay, so nice paragraphs there. Use the terminology I've taught you. Use your critical thinking skills. Okay, so tell me, are you convinced based on what Kendi said? That's a number 9. And then what questions do you still have? This is where we really get into critical thinking. So you type all this up, okay? Type up this page, and then you go back in and delete everything else. I don't want to see pages 1 through 7 again, right? I've got those. So just turn in pages 8 and however much further it goes. It might get up to 10 pages or so. You're just turning in 2, maybe 3 pages, and you're turning those into Turnitin.com. And then I will grade them from there. And again, you know, check with me in class to see when this is due. Okay, does anybody have any questions about this? I guess you can't answer it because it's recorded, but that's just my reflexes to ask if there's any questions. Get in touch with me if you do have any questions. And thanks for your time. Good luck.